Okay, get started.
All right, sounds good. So, hi everybody. My name is Ari Israel, or Ariel Israel, if you want to go by my full Zoom name. Um, I am actually a double Blue Stamp alum. I was a Blue Stamp student in New York in 2016, I think, and an instructor in 2019. I worked with Jesse in New York also. Um, and I currently am a sophomore studying electrical engineering at University of Maryland with a minor in computer engineering. Um, and basically, my engineering journey sort of started when I went to Blue Stamp. I knew I always liked science and math and building things. And going to Blue Stamp told me, oh, this is engineering, this is cool. Um, but I still didn't really know what type of engineering I wanted to do. I didn't really know the difference between any of the types. I heard the terms electrical, mechanical, civil, but I didn't really know what the difference was between any of those. So I'm studying electrical because I wanted to do, I knew I wanted to do something with computers, but I knew that I didn't want to do only software. I knew that I didn't want to be coding the entire time. So electrical offered me a way to be doing both the hardware components, meaning like the circuits and like how computers are designed and developed, and power sources and things like that, as well as having exposure to the brains behind it, the coding, the vehicle, the coding different things, and being exposed to both of those things showed me that I was really interested in both of them, and being able to merge them would be a good fit for me. So that's why I'm studying electrical engineering. University of Maryland is a very good electrical and computer engineering department. So learning a lot, working hard. Unfortunately, I'm not in College Park right now, as I'm sure we're all dislodged a little bit from where we normally are, but still class is continuing. Anything else about me that's interesting? I've taken a lot of cool classes and I've learned a bunch of different things. I've focused on, in terms of coding languages, I know C, I know MATLAB pretty well, C++, and then a bunch of other random things. And I've taken some cool hardware classes like circuits, digital logic design, and if you guys have any questions about what those are, I definitely did not know when I was in high school. Feel free to ask me at any point. And yeah, if you actually have any question in the middle, feel free to either unmute yourself and ask or type in the chat. I'm going to share my screen in a minute, so if I don't see, you can just call it out. I'm happy to answer. But now I want to bring you to a project that I worked on. It was actually part of one of my classes. It was the Intro to Engineering Design class. And I'm just going to share my screen and we'll go straight to it. Can you guys see that? Yeah, okay, great. So, I'm just going to make sure I can see you guys. Okay, so this is a project that I worked on. It was actually a group project, and for the project we had to create something called an oversand vehicle. So here is my team. You can see me right here, and this is what we created. And basically, the way that the class was organized was that we were split up into a team on the first day, and the team was made up of people of all different disciplines of engineering. So I was an electrical engineer, we had a computer engineer, we had chemical engineer, we had a bioengineer, we had 2 mechanical engineers, and it was really just a split of people across all disciplines of engineering who we could really help each other. But we're all pretty new to the engineering sort of game, and we were all very early in our engineering careers. And the premise of the project was that they created this course. This is the obstacle course. And basically, the goal of the course was to create a vehicle that could navigate autonomously, that means without a remote control or without us doing anything, to the mission site. And then at the mission site, it would do something. So a bunch of caveats. So first of all, the vehicle started in a random place anywhere in this landing zone. So it would be given a random y coordinate and a random theta direction, meaning it would face one of the 4 cardinal directions, and it could be placed anywhere in the landing zone. And the same thing was true for the obstacles and the mission site. So the obstacles were given a random xy coordinate, and I guess the angle doesn't really matter, but they were placed anywhere here. And the mission site as well would be placed anywhere on the board, but it would be on the last sort of trip of the last sort of strip of the board. So given that the board was randomized each time, so we couldn't really have a set algorithm to just travel through the course. Another thing that was interesting was that this course was set up with something called a vision system, that it basically had a camera on top of the board that would track a QR code that would be on top of each vehicle. So this way, the computer system, it would generate the original XY coordinates, and it would basically tell us where in the box to place the vehicle and where to place the obstacles. But also, since we had a QR code on our vehicle, we would be able to track the device as it goes, and it would report what its XY coordinates were and what its theta coordinate was, its angle. So basically, we had to figure out a way for our vehicle to locate basically where it was on this landing zone, get to a point where it would be at the same level as the mission site. Then it would turn itself forward. And obviously, depending whether it was going down, it would need to up or down, it would need to turn different ways. Then we had this rough terrain that it would need to go over, that it needed to have enough torque that it could clear these like sort of quote unquote mountains. Then once it got to the second half of the board, it would need to continue straight until the mission site, until it detected an obstacle. Then if it saw an obstacle, it would have to do some sort of detection and then move around the obstacle. So this, we used different sensors, and we created an algorithm for it to go around the sensor and then get back on the correct path and make its way to the mission site. So once the vehicle got to the mission site, we had, there were different objectives for different groups. My group was the water sampling group. So when we got there, we had a few different tasks. The first thing we had to do was check the pH level of the water and check whether the water was quote unquote like polluted, which meant like, did it have food coloring in it, or was it clear? And then also to check the depth of the water pool that was there. Then when we received this information, we would have to transmit it back to the computer, back to the system, and print it out on a console that was part of this program. The next thing, the last thing that we had to do, which was extra credit, but we actually were able to do, is we had to take a sample of the water on board of our vehicle. So there was obviously a lot to do, and there were many different parts of this project. So here is the vehicle that we created in order to do this task. We called it the H2OSV, because H2O obviously is water, and OSV is the oversands vehicle, which was the thing of the project. So I'm going to walk through with you a couple of these parts, and I'll tell you specifically what I was working on. So the main brains of our computer, of our H2OSV, was the Arduino Romeo. So I'm sure some of you have heard of an Arduino. You can't really see it here. Arduino Romeo is basically a special Arduino that has these built-in motor drivers, these motor shields, in order for it to be able to power motors. As you can see, we have 2 sets of wheels on each side, or a set of wheels on each side, I guess. So we needed motors for each of those. And we also needed to power a servo motor in order to lift and lower this arm. We obviously used breadboard to help with connections, and a power source. We had batteries, you can't really see here, but it's right over here, in order to power the whole board and to make it actually run. We also had an RF antenna, as you can see here. So an antenna, you might know, allows you to communicate with something else. So this antenna basically connected through Bluetooth with a different antenna that was connected to the computer system. So this was the way that we received the coordinates of where we would put things, and we would transmit the coordinates of where we were back to the computer, and also how we would transmit the information based on the pH level of the water and the depth of the water. We would transmit it back through this antenna. So the RF communication allowed us to have communication back and forth with this computer screen. So I mentioned them a little bit earlier. We had the 4 DC motors and the non-continuous servo motor. So the DC motors obviously were in each of the wheels. They helped us move. And the servo motor would raise and lower this arm. The reason we decided to use a non-continuous servo motor, so I'll just explain quickly. There's 2 types of servo motors. A servo motor can either be continuous or non-continuous. If a servo motor is continuous, that means that it can turn to a certain position just based on the amount of time that you leave it on. So it will just keep going based on timing, and it can turn more than 360 degrees. It'll just keep turning. A non-continuous servo motor, you tell it to turn to an exact angle, and it will just turn to that. And that is more precise, but it doesn't let you go to as far of a range because it typically stops at 180 degrees or something like that. Also, we had this DC motor pump. The way that a pump works is very similar to the way a motor works. So this peristaltic pump, it's called, which got the water on board and put it into this dish in the back, basically just turns a motor to create suction and pull up water through this tube and to get it on board. The last thing I want to point out is the sensors. So ultrasonic sensor, that's these guys. I'm sure you've seen these if you've worked on, if you've looked at your kits and you've done similar projects. The ultrasonic sensors basically test distance. They send out a pulse, and based on how long it takes to come back, they know how far away objects are in front of them. So we use that to navigate the course. I mentioned already the pH sensor and the depth sensor and the salinity sensors. These are all on the arms here. And they all basically work with some sort of type of resistance. For example, like the depth sensor has these like copper pads on them, and whether based on how high the water gets up, we know where the conduction levels are, so we know how high the water is at that point. That's basically the main parts of the vehicle. So as an electrical engineer, and I had one partner who was a computer engineer, so we basically worked in tandem. In terms of the hardware, we were in charge of all of the wiring and also the communication to the vision system. So all the wiring you see here and all the organizing, that was a large part of what I did. And basically the way that we did that is we worked in pieces. So I focused a lot on the navigation stuff. So I was working on the motors and connecting those to the breadboard. And then eventually the code, I'm going to get to that also. And I was also very big on working with the communication to the vision system. So I worked a lot with the RF sensor, tested that work. I tested that we'd be able to receive coordinates and travel to those coordinates. And based on where we were, we'd be able to do certain things. And that's a large part of what I did. Obviously, another major part of our operation was working with these sensors. Thankfully, there's a lot of work that's been done with these sensors. So there's a lot of good examples of stuff online. So we basically worked off online examples for using these sensors and then merged them together all into our code. Now I just want to go through one of the coding problems that we ran into and basically how we solved it. So I was working mostly on the navigation code as opposed to the mission site code. So I'm going to walk through that a little bit. So this might get a little confusing, but one of the problems we had was with turning within the course. So I mentioned earlier that the system that we were working with provided us with an angle which the vehicle was facing, right? So at any time it would tell us which way we were facing. However, the system was a little bit weird because it basically gave us an angle from 0 to pi. And then right after pi, it went to negative pi. And then it went negative pi to 0. So if you can imagine it like this, I don't know if you guys have learned radians yet, but basically radians are another way of keeping track of degrees, or like how big, like the angle that you're in, besides degrees. So there's 2 pi radians in one circle. So instead of going from 0 to pi to 2 pi, it went from 0 to pi. And then if you went the other way, it went 0 to negative pi. So this doesn't seem like a huge issue, but it sort of came into the front and affected us a lot when we were working on turning. Because basically, let's say we wanted to face to turn this direction, we wanted to face to turn the right. We would say something like, if theta is greater than pi over 2. So that means if theta is, typically if theta is greater than pi over 2, that means that theta is anywhere between the way facing up to the way facing all the way back here, right? Because pi over 2 is here. But in our system, because down here is all negative, anything down here, even if it was in this quadrant, the third quadrant, it would still be smaller than pi over 2 because it was considered a negative number. So that was a hard challenge that we had to figure out. And the way that we worked around it is that we used absolute value. So the code's a little bit confusing, but I'll try to walk you through it quickly. So the first thing we did was check if our location of the vehicle right now was greater than the destination y, the y coordinate, or it was less than the y coordinate. So basically, we would be able to tell if our vehicle was above or below the destination, and based off of that, we would know whether we wanted to go downward or go upward. So let's say we were above the destination. That means we would want to turn down. But we wanted to go, because we had a set amount of time, we wanted to turn in the most efficient fashion. So then we used what I was talking about earlier with the absolute value. So if the absolute value of theta was greater than pi over 2, which means it was facing leftwards in some way, either up and left or down and left. I'm sorry, it's a little hard to explain, but that means it was either facing towards the second or the third quadrant. Then we would turn left, because that would be the fastest way to turn down. However, if it was less than pi over 2, then we would turn right. And we did the exact same thing, but opposite if the vehicle was beneath the final destination. I'll just finish up here. So then basically once we were either facing up or down, depending on whether we were above or below the final destination, then we would go forward until we reached that y destination with a little bit of a buffer, just so we didn't go too far forward. And then we would basically stop, and at that point we would turn towards the rest of the course, and we would continue. So I will just finish up with a short video of our results. So here you can see our vehicle. We right now determined that we were facing closer to this direction, but the result, it's going to be, the destination is at a higher point than we are. So we basically want to turn to face upwards in the box. And now we've determined that we are facing upwards. We're going to continue going forwards. So here we go. We're going to keep going. And the reason we decide to move like this, that's in like a very lurchy fashion, is because the vision camera system was not very quick. And if we went like very continuously and fast, the camera wouldn't catch it, and we would go past our destination. Here you can see the whole course is covered in sand. So we had our mechanical engineers were worked very hard on the calculations to work on what kind of motors and what kind of wheels we were, so we wouldn't get dug in or anything like that. See, we almost got dug in here, but our vehicle makes it all the way around, faces the right direction, and continues over this mountainous area. And it's going to continue forward. Lurches a little bit off, but corrects itself. And here you see the mission site. We're going to make it in. and we're gonna dip our arm right in. And then you can't see this, but right now we are measuring this stuff with the sensors, and we're gonna use this antenna right here to submit the information back to the computer screen, which was guiding us the whole time. So that is basically it. Let's see if I know. That's it. So that's basically all from me. If anyone has any questions, I'd be happy to answer them. It could either be about me or about my project. And yeah, thank you guys for listening.
Does anyone have questions? I think everyone's muted right now. So if you have questions, you can unmute yourself. Anything about the project or college or Blue Stamp or anything?
Hey, Ari, are projects that students build during the summer at Blue Stamp similar to this, or do they use some of these same technologies?
Yeah, it's a great question. So when I was a student at Blue Stamp, I worked on a remote control tank. So I was familiar already with a lot of the techniques that we used. It was still very different because this was an autonomous project, and a big part of it was working on the autonomous parts and the way of it navigating. But in terms of like the terminology and the structure of how to go about the process, yeah, they were definitely very similar. And it definitely prepared me a lot for this.
Cool.
I have a question too. How did you go about kind of making your decision of which area of engineering you wanted to go into? Was it just that you wanted to work with computers that kind of sent you towards electrical, or was there anything else that you thought about?
So it was mostly the fact that when I was at Blue Stamp, the parts that I enjoyed the most were the Arduino parts. So I liked the building the circuits. I liked the trying different things while connecting things. I liked working with the multimeter, and I also liked the coding part. I liked the being able to do it together and integrating them and working on both pieces of the puzzle. So for that reason, I decided electrical would be a great fit for me because I would be able to have exposure to both the circuitry parts, but also to the coding parts.
Mm-hmm. Cool.
So,
oh yeah.
So you're going into your junior year this year, is that right?
Yes.
Yeah. So apart from this project, how many other projects have you built in college?
It's a good question. So I'm still working a lot through my prereqs in terms of classes.
Yeah.
So it's been a lot of hard nitty-gritty math things, but taking some more classes next semester that I'm very excited about that are going to be more building based and stuff like that.
Okay, cool.
Thanks.
Yeah.
I was going to ask if you had any advice for students that are looking to kind of go from high school into college as an engineering major.
Yeah. So college is hard, especially engineering in college is very hard. I just recommend it's hard, but it's doable. If you work hard and stay diligent and make sure you're on top of your work and go to office hours and make sure you really understand the material, it's very rewarding, and you learn a lot, and it's very cool. And then you have classes like these that are not only challenging but also fun and interesting, and that's the rewarding part of engineering.
Awesome. So if there's no other questions, I think that it's about time to wrap up. Any last questions from our guests? Our student guests? No, it doesn't look like it. Well, Ari, thank you. Brianna set this all up. Thank you, Brianna. Thanks to our guests who came in for the talk, and I'll be uploading the talk on YouTube, so you can kind of check it out again if you want to see the slides about Ari's project. But otherwise, yeah, thanks everybody. Hope you have a great evening.
Yeah, thanks so much, guys.
For listening.
Cool. Bye.
Bye.